In this video, we are going to explore the concept of the mole and chemical formulas. We saw previously that we learned the relationship between moles, atoms, or molecules. If I go back to the flowchart on on slide 13, we can see that we can relate specifically the unit of moles to the grams of elements or formulas. Our conversion factor when it comes to this is going to be the atomic mass, or in other words, the molar mass for a particular atom or compound. So how do we achieve this? When it comes to chemical formulas, we can actually calculate what is the molecular weight of the whole system by taking into account, based on the chemical formula, the number of atoms that we have, and we're going to multiply it by the atomic mass that shows up in the periodic table for that particular element. So if we take, for example, CO2, CO2 is composed of one carbon, and this is the atomic mass of carbon. You can see that the unit is AMU for atomic mass unit. And in CO2, we have two oxygens. And this is the atomic mass for oxygen. So when I take 1 times 12.011 plus 2 times 15.999, and I add them, this is the total number that I get from adding those two values, which is going to represent the molecular weight for CO2. So, since we know that the molecular weight of the compound is related to moles, this molecular weight that we determine equals 1 mole of that compound. In other words, 1 mole of CO2 is 40.00 AMU, or 1 mole of CO2 equals 44.009 grams of CO2. To calculate the molecular weight for compounds, as we can see, we have 3 examples in the bottom. I'm going to do specifically letters A and B. In letter A, we have rubbing alcohol. For rubbing alcohol, in terms of carbon, I have 3 atoms of carbon, and I'm going to multiply that by 12.011 AMU, which is the mass of carbon in the periodic table, plus I have 8 hydrogens, and the mass of hydrogen in the periodic table is 1.008 AMU. Lastly, I'm going to add the oxygen. I only have 1 of them in this chemical formula, and the mass of oxygen is 15.999. So when I take these 3 different amounts and I multiply the values by the subscripts, essentially, that we have for the atoms, I have 3 times 12.011, and I'm going to add that to 8 times 1.008, and I'm going to add that to 15.999. That means that the molecular weight for rubbing alcohol is going to be 60.096 AMU. In other words, 1 mole of rubbing alcohol is going to equal this mass. Let's now do the one for baking powder. Baking powder, which is ammonium carbonate, has the following chemical formula. In this molecule, I have nitrogen. And to determine how much nitrogen I have to remember that since there are 2 outside, then that means that 2 gets multiplied by the subscript of the nitrogen and also by the subscript of the hydrogen. So in this chemical formula, I have 2 nitrogens. The the atomic mass of nitrogen is 14.007 AMU. I'm going to add that to hydrogen. Let me erase the atoms because I didn't do it for all of them, but I hope that you follow the work that I'm doing. Next, let's count how many hydrogens we have. We have 2 times 4, that's 8. So we have 8 hydrogens in the system. And the mass of hydrogen is 1.008 AMU. Plus, we have in the system 1 carbon, 1 times 12.011 AMU. And lastly, we have 3 oxygens. So we're going to do 3 times 15.999, which means that specifically, when we add all these amounts, 2 times 14.007 plus 8 times 1.008 plus 12.011 plus 3 times 15.999. The mass of ammonium carbonate, I'm going to write it right here, is going to be 96.086 AMU. In other words, in 1 mole of baking powder, we have 96.086 grams of baking powder. So now let's see how we can utilize this number in conversion factors. We can see that in the following practice problems, we are trying to find in letter A, the mass in grams of this particular amount of moles. So for letter A, I am given moles and I need to look into grams. So if I go back to slide 13, I see that if I'm given moles and I need to get to grams, I'm going to basically multiply by the atomic, in other words, the molar mass. Remember that it is called molar mass because those grams equal 1 mole. So when I go back to my problem, I am given 1.62 moles of CO2. Since I know that 1 mole of CO2 equals this mass, then I can write in the bottom 1 mole of CO2 equals 44.009 grams of CO2. The units of mole cancel, and then my standing unit at the end of the problem is going to be grams. So if I take 1.62 and I multiply it by 44.009, I find a calculator display that says 71.29, and there's a rest of digits. Since I was given 3 sig figs, I need to write my final answer with 3 sig figs. So the final answer is 71.3 grams of CO2. In example B, we have to discover what is the number of molecules of CO2 in 63.9 grams of CO2. So to set up letter B, we're going to write down the amount given, 63.9 grams of CO2. And if we go back to slide 13, if I am given grams and I need to go to moles, I need to divide by the molar mass. So when it comes to this, I'm going to write in the bottom 44.009 grams of CO2 over 1 mole of CO2. That means that when it comes to unit cancellation, the grams of CO2 cancel with each other. And when I take 63.9 and divide it by 44.009, I see that my calculator display says 14519, and there's a series of digits. Because I was given 3 sig figs, that means that my final answer will be rounded to 3 sig figs. So this is 1.45 moles of CO2. If I zoom in into the right side of the slide, we can see again the flow chart that we have been utilizing to change from moles to molecules in atoms and vice versa. And as recently, we used to change moles into grams. Because of this chart, you can envision that we can change all the way from grams of something to atoms or molecules of something. And in the first example that we have here, we are going to try to find how many molecules we have present in 3.36 grams of molecular fluorine. Since we are given grams and we need to go to molecules, we just have to follow the arrows to understand what are we doing in our mathematical equation. So we can see that if we're going to do grams and we're going to achieve getting into molecules, I have to convert from grams to moles. Then from moles, I get into the molecules. So I'm going to follow those arrows. To set this up, I know that I'm going to divide by the molar mass and I'm going to multiply by Avogadro's number. So this is how I set up my problem. I'm going to write 3.36 grams of F2. As you can see, I'm going to divide by the molar mass, and I already have written the molar mass, which is 37.996 grams of F2 in every mole of F2. Next, I'm going to multiply by Avogadro's number, meaning that in the bottom of that second fraction, I'm going to write 1 mole of F2 corresponds to specifically 6.0, let me fix this digit, 6.022 times 10 to the 23rd molecules of F2. So in order to find the answer, I'm going to take 3.36 and I'm going to multiply it by 1, and I'm going to then multiply it by Avogadro's number, 6.022 times 10 to the 23rd. Then I'm going to divide that by 37 0.996. And my calculator display, when rounded to the correct number of sig figs, which is 3, shows me that the answer to this problem is going to be 5.33 times 10 to the 22 molecules of F2. It's what is present in 3.36 grams of molecular fluorine. Let's do one more example in which now I am giving molecules. It could be atoms too, but then I need to find mass. When it comes to this, we can see from our flow chart that if we're given this number and we're trying to find grams, I have to divide by Avogadro's number, followed by multiplying by the molar mass. So to set up this problem, this is 2.75 times 10 to the 24. So as a first step, I'm going to divide by Avogadro's number. 6.022 times 10 to the 23rd. And this is going to be molecules of N3O7, which is trinitrogen heptoxide. This is going to be molecules of N3O7 and 1 mole of N3O7. Next, I'm going to use the molecular weight, which I already wrote it down, in order to find the grams. So I'm going to write 1 mole of N3O7, and then on top, 154.014 grams. And when I do this, what I have to do is 2.75 times 10 to the 24 times 1 times 154.014. You're going to divide that result by 6.022 times 10 to the 23rd. And I find specifically that there are 703 grams of N3O7 when I start with 2.75 times 10 to the 24 molecules of it.